Good morning, my name is Alan Andonian. Today I will be presenting vortex shedding in two-dimensional flow around two cylinders. This is for partial fulfillment of my master's thesis. As a brief outline, I will be starting off with introducing the problem of this thesis. I will follow by describing the mooring line setup and the associated natural frequencies. Then I will go through the single cylinder simulations and the two-cylinder simulations. I will conclude with the results of the simulations and how they apply to the real-life problem. For the introduction, I would like to give context to the background of the thesis. Let me start with the water cycle. The water cycle is an important part of the overall global heat and moisture transport. Observations of the global water cycle are important to monitor climate change over the decadal and millennial timescales. With the rise in global temperatures, there will be more water vapor in the atmosphere, which increases the potential for extreme weather events. To understand the change in global hydraulic cycles, we first need a good baseline for global precipitation. The current report by the Intergovernmental Panel on Climate Change states that there are large uncertainties in water cycle projections in the future. Even the current precipitation amounts are not well constrained, especially over the global oceans, which collect 78% of all precipitation. It is essential to have accurate rainfall measurements over the sea at multiple timescales to monitor climate change and its impacts. There are optical rain gauges and capacitance rated gauges that operate on ocean platforms, which provide in situ measurements. However, there is a high infrastructure cost to the ocean platforms, which limits the scope of the measurements to a small number of ocean buoys. There is also a global rain dataset that has been computed based on rain gauges on ships. However, this study is limited to the maritime travel routes taken by the ships. The ships do not cover the entire ocean and have a fair weather bias. Satellite data can provide broad coverage of the precipitation on the world's oceans. However, there can be an uncertainty in the satellite data of 100 to 140% and large uncertainties in the coastal regions. Acoustic rainfall gauges provide a simplistic solution with stable calibration characteristics. The Global Drifters program provides scientific data of in situ measurements for a broad array across the world's oceans. If they were to be instrumented such that they could yield rainfall rates over the ocean, that would be a fundamental advance in measurements of rain globally. To develop in that direction, the parent project of this thesis, supported by the Marine Underwater Science and Technology program at UMass Dartmouth, has aimed to instrument an acoustic rainfall gauge first at a fixed location. The overall goal is to have rain gauges on the Global Drifters program drifters to provide scientists with a broad array of in situ measurements of rainfall. This will make for a denser coverage of in situ measurements that can be used simultaneously with satellite data to give scientists a more accurate picture of the Earth's water cycle. Further, this would eventually help monitor climate change, as well as be used to predict extreme weather events. The mooring assembly is made of various sub-assemblies of marine-grade hardware. The swivel shackle allows the mooring buoy to rotate with the normal currents. The recording device is placed at about 15 feet depth, and the mooring assembly is placed at about 30 feet of water. The depth of the water is important to prevent potential echo from affecting the acoustic measurements. The weight of the chain resists the buoyancy of the buoy, which creates a natural tension in the line. From the tension in the line and the properties of the mooring line, we can determine the natural frequency of the system. We find the natural frequency of the system to be 1 to 7 Hertz. Knowing the natural frequency of the system, we can assess the system to see if there will be an external force from normal currents that could cause the mooring line to have harmonic oscillations. This could lead to failure and fatigue of the system. How does a vibrating mooring line create sound? Well, when a current passes by a mooring line in tension, there is the potential for vortices to be generated, which can lead to an oscillating lift force on the line. The vortices are actually low pressure regions that travel downstream. The pressure waves can be picked up by the hydrophone as sound. If the sound is in the acoustic range of rainfall, this can be a source of acoustic interference. Given the correct flow conditions are provided, there can be an asymmetric vortex shedding downstream of the mooring line. That is, when the flow goes past the mooring line, the viscous forces on the fluid tend to attach to the surface of the line. This creates a boundary layer. Upon further development of the boundary layer, the layers can begin to separate, which can then create a trailing vortice. These vortices are the source of the oscillating lift force mentioned earlier, which can lead to vortex-induced vibration of the mooring line. Furthermore, to aid in the investigation of the system, the mooring cable can be approximated as a cylinder. Assuming that the flow is uniform throughout the length of the mooring line, and the density throughout the body of water is constant, the 3D cylinder can have a 2D approximation. This is an appropriate approximation given the well-mixed layer of the ocean is usually much larger than the length scale of the mooring line. The two primary non-dimensional numbers used for the two-dimensional flow are the Struhal number and the Reynolds number. The Reynolds number is used to characterize the flow, and the Struhal number is used to track observations of the vortex shedding frequencies. The Struhal number has been well cited for almost 2 centuries for the flow past the cylinder problem. Given the dimensions of the mooring line, and that the Struhals are usually around 0.2, I found the expected range of frequencies, shedding frequencies, to be 1 to 20 Hertz, and the expected Reynolds range to be around 250 to 5,000. This preliminary investigation shows that the expected frequencies may be outside the acoustic range of frequencies for rainfall of 1 to 30 kHz. However, further investigation using computational fluid dynamics is explored. The numerical model setup is shown here. A uniform velocity flow comes from the left side through the inlet, shown here in blue. The top and bottom walls have a slip condition, shown here in yellow. The slip condition is used to create a bulk flow past the cylinder. This was done to mimic the flow past a mooring line in the ocean. The domain size of the numerical model was determined after a series of sensitivity studies. First, I varied the inlet height and monitored the lift coefficient and the Struhal number. And when I see the screw hull or the lift reaches a stable solution, then I know I have a suitable inlet height. It was found that an inlet height of 15 diameters was suitable. Similarly, a sensitivity study on the position of the inlet relative to the cylinder was performed. The results of this study show that the inlet should be placed no less than 5 diameters away from the cylinder. A mesh dependency study was also performed, and it was found that a fine mesh density was sufficient for lower Reynolds number of around 100. However, when the Reynolds number increased to 5,500, an extremely fine mesh was used. The time step of the simulation was also assessed to see if changing the time step would affect the screw hull or the lift coefficient. The vortex shedding period was first determined from an overprediction of the screw hull number, and then the analysis was performed using increments of how many time steps per shedding period. Although there is not a definite time step that should be used based on this study, it was chosen to use 6 time steps per shedding period. This is enough to meet the Nyquist criteria, which states that there should be at least 2 sampling periods per vortex shedding period in order to accurately predict the vortex shedding frequencies. After the sensitivity studies, the results of the simulations are shown here. On the left, we have the non-dimensional vorticity for Reynolds of 100, 700, 1500, and 2000. The Reynolds of 1500 and 2000 show similar shedding patterns. However, the Reynolds 2000 case is further in time and shows a more developed shedding pattern. At this Reynolds number, once the flow is developed, there appears to be 2 sets of vortices coming from the flow past the single cylinder. The time series of the fluctuating lift coefficient and the power spectra are also shown here. Note that the dominant shedding frequencies are around 0.2, which is to be expected based on literature values. Capturing the dominant shedding frequencies from the power spectra, we are able to plot the non-dimensional vortex shedding frequencies, or the screw hull, against the Reynolds number. When we compare the works of Norenberg and Tyler, we see a good correlation between our numerical model and the literature values. This gives us confidence in our simulations and allows us to further develop the model for 2 cylinders. Going back to the real-life mooring problem, if we put the shedding frequencies back into dimensional terms, we see that the vortex shedding frequencies are about 2 to 3 orders of magnitude smaller than the acoustic frequencies associated with rainfall. This is good news because there is less potential to have acoustic interference. To further develop the simulation and increase the accuracy of the solution, a multi-body simulation is developed. This simulation has 2 cylinders, one representing the hydrophone and the other representing the mooring line. We investigate whether there could be a combined effect when the wake of one cylinder amplifies the wake of another cylinder. This could cause a larger frequency which could get closer to the acoustic frequency of rainfall and interfere with the acoustic measurements. This could reveal if the mooring setup needs to be redesigned to prevent acoustic interference. Because of the complex nature of the flow past the 2-cylinder configuration, often the first and second peaks of the power spectra are taken as the screw hull number. In the figure on the left, we see 2 screw hull numbers for each of the experiments. You can see that there is some variability in the results. This can come from a large variability in the method of measurements for each of the experiments. Sumner et al. Uses movie frames of the flow pattern to count the vortices over time. Hugh et al. And Kaya et al. Use hot-wired measurements. Alam and Sakamoto use a pressure transducer. With all the different forms of measurements, in this thesis I tried to standardize how I measure the Struhal number for a two-cylinder configuration. I do this by taking the first dominant frequency of the power spectra associated with the maximum power, and I take this from a gridded array of pressure probes in the computational domain. The computational domain selected for two-cylinder simulations has a width of 25 diameters, an inlet height of 17 diameters, and the mooring line is placed 5 diameters away, plus the length between the two cylinders. The larger mooring line cylinder diameter is shown with a capital D, and the smaller hydrophone diameter cylinder is shown as a lowercase d. The angles between the axes created between the centers of each cylinder and the free stream velocity is denoted as alpha. The length between the centers of the cylinder is denoted as L. As a comparison to Sumner et al., a study on the location of the pressure probes was performed. Using 7 probe locations in Y and 4 probe locations in X, it is found that the power spectra can show a second or third peak depending on the location of the probe. For this particular configuration, there is a small gap between the cylinders which allows the fluid to accelerate. This creates a large trailing vortex in the wake of the cylinders. This is the reason you see 2 or more dominant frequencies. Using the power spectra associated with the location of maximum power, we compare to the work of Sumner. For the angles of 0 and 10, we see good correlation for the first frequency. For 20 and 30 degrees, the first peak appears to be closer to the experimental work. For 40 degrees, we see a strong correlation for the first peak. With this comparison, we remember that there could be variability in the results because of the variability in the measurements. With this study, we'll proceed to identify the Struhal number for other Reynolds numbers. Here we examine the flow past a 2-cylinder configuration for Reynolds of 7,000. In this case, we take a gridded array of probe locations, shown here with small dots in the top right image. We then look at where the power intensity of pressure oscillations is greater than half the largest pressure oscillation. In this region, we take our probe locations. As shown here, in the non-dimensional vorticity of a few of the configurations, you can see that the angles of 90 degrees has the most distinct wake for each cylinder, while the angles of 30 and 60 degrees appear to have vortex shedding wakes that interfere with each other. We take the power spectra from the probe locations with the highest intensity of pressure oscillations, and we choose to identify the first 3 peaks of each spectra as the Struhal number. When we compare the Struhal number with that of Hugh et al., we tend to see that the first and third frequencies have a strong correlation to the literature values. When we move to different ratios of the cylinder sizes, we redefine the distance between the cylinders as a variable s. This was done because the interference between wakes depends on the distance between the boundary layers of each cylinder. In order to ensure the surface of each cylinder remains at the same distance, we keep s constant. Shown here, we have the diameter ratios of 1, 0.75, 0.5, and 0.25 for a non-dimensional separation ratio, 1, and an angle of 30 degrees. Note that when the cylinders are the same size, the combined wake appears to create the largest vortices. In fact, when you look at the first Strouhal number of each configuration, the largest cylinder ratio appears to have the largest Strouhal number. That is, except for the angle of 30 degrees, where the 0.5 diameter ratio has the highest Strouhal number. For this configuration, the fluid accelerates through the small gap between the cylinders, and the wake of each cylinder is able to combine. This creates the perfect storm for the largest observed shedding frequencies for that angle. Also note that the diameter ratio of 1 was not done for angles above 90 because the setup is symmetric with a diameter ratio of 1. Now, if we look at the highest Strouhal frequencies we calculated, we see that there are not close to the acoustic rainfall frequencies. However, the vortex shedding frequencies could interfere with submarine communications. This is currently out of the scope of the thesis. On another note, the shedding frequencies are close to the natural frequencies of the system. This means there could be a harmonic oscillation in the mooring line that could potentially have large amplitude noise. This could saturate the acoustic signal and prevent the acoustic measurements of rainfall. In order to prevent saturation of the signal, it would be recommended to add spiral blades to the mooring line. This can interrupt the flow and change the shedding frequency. Another measure could be made to change the mass of the system by changing the mass density of the mooring line or by changing the mass of the recording device. This would change the natural frequencies of the system. Any questions? Here are my references. At this time, I will take any questions.